So we're really happy to have Gunnar giving a talk today in our SIAM Pacific Northwest chapter series. Gunnar comes to us from Sweden, where he did his undergraduate degree in engineering and a master's degree in mathematics on the Sunshine Coast of Sweden at Chalmers University in the southern part of Sweden. Then he went on to several prestigious appointments at Yale, University of Colorado Boulder, Oxford University in the UK, KTH in Sweden, and is now the named Tex Moncrieff Endowed Chair in Simulation-Based Engineering Sciences at UT Austin, University of Texas at Austin. And he's currently an associate, or has been, or is currently an associate editor for several of the key journals that we all aspire to get our papers published in, including BIT and SIAM, Journal of Scientific Computing. And maybe most important for this audience is that he is a SIAM Fellow, class of 2021. He's had numerous NSF, DARPA, ONR grants, has supervised many PhD students and postdocs, including Heather Wilbur, who is Grady Wright's former master's student. And for those of you who don't know, Grady Wright's a former president of the SIAM Pacific Northwest chapter, and his student Heather Wilbur did her master's degree at Boise State, and then went on and did with Gunnar. And of course, he's got many journal articles in a wide variety of journals in areas ranging from very theoretical, numerical linear algebra to software development. I happen to know of his work, sort of at least one tiny part of his work, because I have a student, Damon Chipman, who's implementing the hierarchical Poincaré-Steklov method for solving elliptic problems on adaptive meshes. And it was his work together with his PhD student, Adriana Gilman. They developed a randomized method that enables the HPS method to have order n complexity. And I'm hoping that today we will learn more about his, well, I know we will learn more about his work in randomized linear algebra. So thank you again, Gunnar, and I'll go ahead and let you get started.
Thank you very much. It's really a pleasure to be here, and I very much appreciate the invitation. And so Heather, I have greatly appreciated having her here the last couple of years. She's been here as a postdoc, and I believe she's coming back Northwest, so you may see more of her. Yep. So today I'm going to talk about randomized algorithms for sort of matrix computations, and the first half of the talk is going to be fairly well-established material. So some of you have probably seen it already. And let me stress that most of the work I'm going to talk about that's been recent is joint with my current research group. And so Heather is coming to University of Washington. Right. And the talk, it has two halves, basically. The first one is about this body of work that by now is fairly well established. So some of you will probably have seen several of the slides, most of the slides, in fact. It concerns how to compute a low-rank approximation to a matrix using these randomized algorithms. And then I will talk about some more recent things that I've been playing with over the past few years. We'll see how we're doing on time. So this is, I should aim for 50 minutes, 45?
Yeah, that sounds good.
Okay,
50
great.
Is good.
Yeah. Yeah. All right. So most of the talk will a very basic problem in scientific computing. So we're given a large matrix, we want to compute a low rank approximation to it. So given the matrix A, we want to find some factors E and F that are thin. So let's see if I can get the annotation tool to work. Okay, yeah, so E is thin in this way. I'm mostly doing this just to make sure I know how the annotation works. All right, F has this shape. So you want to compute E and F. And this, of course, has a ton of applications all over scientific computing. Now I'm rusty with the Zoom talks, I find. Okay, are they gonna remain there? Oh, this was not what I intended. Maybe I'll try to do without the annotations. All right. Sorry, I'm totally rusty. All right, so of course, low rank approximation comes up all over scientific computing. It comes up in data analysis, in computational statistics, all sorts of areas. And in this talk, something that's important is that the only error I'm going to care about is that I want the product of E and F to approximate A as well as possible, which is distinct from sometimes you want sort of high relative precision in small eigenvalues, may want high accuracy in specific eigenvectors and so on. These are not the types of objectives I'm going for here. And this is a very classic problem. So of course, there exist excellent algorithms for solving it. The best one by far is to compute the full singular value decomposition of A, and then you truncate it. So there are extremely stable and relatively fast techniques for doing this. You can do this to basically double precision. And this gives you the theoretically best low rank approximation in several matrix norms. The issue here is that it's very expensive. It has cubic complexity in the dimension of the matrix. You can only do this for moderate scale problems. If you have a very large sparse matrix, and the standard technique to do would be to apply some kind of Krylov method. You take a starting vector and you apply A to it, and then you apply A again, and you get a sequence of vectors that represent various powers of A applied to your starting vector. You restrict A to the subspace spanned by those vectors, and then you approximate A within that subspace. And this is in many ways optimal if you ask the question, with a given budget of matrix vector multiplies, how well can you approximate the matrix? So in many cases, a Krylov method will do as well as you can. And then another thing you can do that's sort of for medium-sized problems works very well is you can just do the very first algorithm many people learn in linear algebra, which is how to orthonormalize a set of vectors. You have a basis for a vector space, in this case, the columns of A. You want to build an orthonormal basis for it. So you simply run Gram-Schmidt, which in numerical linear algebra is oftentimes, we think of it as a QR factorization. And all these techniques, they work fantastically well, but I'm going to argue that you can improve on the performance in many environments. So the algorithm I'm going to describe, or at least the starting point, is a very basic technique in the sense that it all fits in one slide. You have the MATLAB code over on the right in green. So what you do is you draw a tall thin matrix omega from, or you can do it from all sorts of different probability distributions. The most, in some sense, optimal way of doing it is to draw it from a Gaussian distribution, by which I mean that every entry is drawn independently from a normalized, standardized normal distribution. So once you have your tall thin matrix omega, you multiply A into it, and you get another tall thin matrix Y that I refer to as the sample matrix. So each column of Y is now a random linear combination of the columns of A. So they all lie inside the column space of A. And the key assertion here, the one potentially controversial and not always true assertion, is that the columns of Y form a good approximate basis to the column space of A. But if we accept that as a given for a moment, then it's clear how to proceed. You take this basis, which is a bad basis because the vectors are all aligned with the dominant left singular vectors of A. You orthonormalize them to get a better basis that form the columns of a tall thin matrix Q. So once you have that, the rest is just basically, it's just massaging the different factors. You project the matrix down to get a thin matrix B, since B is small. So the premise here the whole time is that the rank K of the matrix is much smaller than the matrix dimensions. So B has only K rows. So you can compute a dense SVD of that using expensive techniques, and then you project back up. And the claim is that the factors U, D, and V that result form a good approximation to the truncated exact SVD. Right. And observe again, let me stress, I said it, but let me repeat it, that the steps in part B here, they're exact up to floating point arithmetic. So the approximation error, the critical question is really how good of a job do the columns of Y do in terms of spanning the column space of the matrix A. So notice that they automatically lie inside the column space. So it's a randomized algorithm, but it's a very beneficial way of running a randomized algorithm because you can only miss in one direction. If you run a Monte Carlo technique, for instance, to estimate the area of some complicated region, you can go wrong in both directions. You can overestimate, you can underestimate. So it's very important to have very exact, a very precise random number generator to not have biases. In this case, it's much less insensitive because you can only go wrong in one direction. You can only miss stuff. So in this case, you just do a bit of oversampling and basically that works. So in cases where the singular values decay reasonably fast, this very simple algorithm that I described works very well. If they decay more slowly, then you need to do a little bit of power iteration, as we will see. All right, so let me just repeat. So here I restate the algorithm. It's just exactly the same algorithm as on the previous slide. So now let's look at some numerics. So how large are the errors? So as I mentioned before, I'm only going to measure how close the computed factorization UDV star is to the original matrix A. So here I measure the error in the spectral norm. And then the Eckart-Young theorem, this is what says basically that the truncated SVD is optimal. It says you cannot do better than the k+1 singular value. That's as close as you can possibly get to A if you're restricted to rank K matrices. All right, so here we have a matrix that it's a discretized scattering operator, and its singular values are the black line. So notice that it's a log scale, so they stay flat for a while, then they decay very rapidly down to floating point precision, and then of course nothing happens since we're computing things to 15 digits. Right, so the red line here represents the errors you get if you run the randomized SVD that I had on the previous slide. So in this case, where the singular values decay very fast, it's very efficient. It's very accurate, I should say. It gets very close to the optimal errors. But you can get even closer if you incorporate just a little bit of power iteration. So the idea is, in the original technique, I didn't have this prefactor. Do you guys see my hand moving on the screen? Okay. So on the previous slides, I did not have this factor in front. And that works well when the singular values decay rapidly, as they do in this case. But if you want even higher precision, you apply a couple of additional powers of A. So there are two additional lines representing Q equal to 1 or 2. So either one application of A, 3 applications, or 5, basically. So I'm not assuming that A is symmetric, so I have to alternate A and A adjoint. But in this case, you basically nail the errors with just a very modest amount of power iteration. Here's another example where the singular values decay more slowly. And in this case, you really do need the power iteration to get close to optimal errors. The red line is what you get without power iteration, and we see that it performs quite poorly. Right, so now the next thing to think about is that this is a randomized algorithm. So every time you run it, you get a different output, because each time you run it, at least in theory, you code it. This may or may not happen depending on how you run your random number generator. But at least in theory, the first step is to draw an instantiation of the Gaussian random matrix. You get a different one each time, and the output depends on your draw. So each time you run the algorithm, you get a slightly different answer. So in order to analyze it, we have to use probabilistic methods. So I try to capture that in this slide by showing you 100 instantiations that are all drawn in the same plot. And then the red line is the empirical average of these runs. So you see that there's a little bit of variation. Sometimes you do a little bit worse than you would hope, but basically it's very tightly concentrated around the average, which is really why this works well. If you have slow decay in the singular values, then you get a little bit more variability. Between each run, you get a little bit more deviations from the average. So in order to analyze this, you have to rely on probability theory. And you can prove theorems that says things like this, that the expectation of the error is bounded in certain ways. And what's the main point of this slide is that if you measure things in the Frobenius norm, then you really do quite well, because if we didn't have this prefactor here is the suboptimality. This factor on the right, the sum, the square root of the sum, this is the minimal error as given by the Eckart-Young theorem. So this factor is the suboptimality, and if you do, so P represents how many extra samples you draw. I mentioned earlier that you need a little bit of oversampling. So if you draw, say, K extra samples, you get a factor of √2, suboptimality. Now, if you do things in the spectral norm, it looks much worse, because then what I would want on the right-hand side is to just have this factor. So if it was just the first term, then I would be very happy. But I also have the second one. I have to pay the price of the Frobenius norm, which is much worse. So the error in the spectral norm here is not particularly good. And this in cases where at least in cases where the singular values decay slowly. If they decay very rapidly, then this sum is dominated by the first term, and you get back basically to the beneficial situation. But in cases where the singular values decay slowly, you get a suboptimal error, and this is where doing a little bit of powering really helps, because that really increases the decay of this geometric sum. Well, it would be a geometric sum if you have exponential decay in the singular values. But right, you want to really push down the small ones. So just as a little flag, what we've been doing lately, there's been some work on doing better estimates of the singular vectors. So the theorem on the previous slide, this work is 10, 15 years old, but more recently, Saibaba and then we have looked at the accuracy of singular vectors. And I'm also right now very interested in doing a posteriori error analysis, because if we look at the theorem on the previous slide, you see that the stuff on the right-hand side involves the exact singular values, and you don't know those. So this is interesting for understanding how the algorithm works, but if you run it for some specific matrix, it's not very helpful, because basically you don't know what the singular values are, so you don't know the right-hand side. So what if you plug in your computed singular values on the right-hand side? Heuristically, that should give you some idea what's going on, but of course, you have a chicken and egg problem here, and we're trying to resolve that. What are things you can do? And one way around this is to use a randomized norm estimator to estimate the residual that you've incurred in any specific instantiation. All right, so just to summarize on this basic algorithm, why should you care? What's the advantage compared to the deterministic methods, the classical ones? So a key advantage is that the way that the randomized SVD interacts with your target matrix A is only via the matrix-matrix multiply. So I have one here in step 2, and then I have a second one in step 4. But those are the only 2 interactions with A. And the matrix-matrix multiply is very efficient. So you can do it if the matrix is stored in RAM. This is done very efficiently using BLAST3 operations. If it's sparse, then the advantage is that you apply the sparse matrix to all the vectors in one go, as opposed to a Krylov method where you need to revisit it. So you need to reload the matrix into memory each application. Here it's just one loading on the matrix. So it's very fast in many environments. And the slower your memory is, the more it gains. So a particularly favorable environment for us is a matrix that's stored on a hard drive or a large distributed system or something like this. But so far, everything I've told you provides no gain in terms of asymptotic flop count. The complexity of the method that I described is O of M and K, and this is the same as the complexity of Gram-Schmidt, for instance, if you run it for K steps. But using randomization, you can reduce the asymptotic flop count as well. So you can reduce this K factor down to log K. And the trick here is to use a random matrix omega distribution that has some kind of structure. So you could use, for instance, restricted trigonometric transforms that you can apply using the FFT. You can have things like chains of Givens rotations. I'll return to that point later. And one that I find particularly compelling is a sparse matrix. So this looks as follows. So envision A as your target matrix. This is the matrix we try to approximate. Then you draw an omega that's sparse. And the way this is sparse is that on each row, I'd pick just 2 non-zero entries at random. So what that means is that each column of A contributes to precisely 2 randomly picked columns of the sample matrix. And if you think about it, you see that this matrix multiply can be computed in just 4mn operations, right? There's no k dependence at all, no log k, nothing. Now 2 is pushing it a little bit. This is, you can sort of get away with 2, but if you go up to 3 or 4, this actually works very well. And this can also be efficiently coded. Finding an efficient implementation of a subsampled FFT is quite hard. It doesn't exist in many packages, but multiplying by a sparse matrix is a much more common operation. So this is a very fun, structured random embedding. And it works basically as well as Gaussian in most practical cases. All right, so another thing you can do here is that you can, so in the basic algorithm I show on the top, we interact with the matrix A twice, as I said. First you apply it to omega, and then you apply it to the computed matrix Q. So there are 2 passes over the matrix. You need to read it from memory twice, basically. But you can do away with this. You can actually get away with reading it only once and applying randomized projections on both sides, and then reconstruct the matrix from your sketches. And this is not possible to do with deterministic methods. And this is really cool. If you have an enormous matrix, you can't even store it. It just streams past you, and you only get to see each entry once. You cannot store it. Then you can actually compute a low rank approximation using these randomized techniques, assuming that you have an upper bound for the rank in advance. If you don't, then I don't think it's solvable otherwise. Right, okay, so that's what I wanted to tell you about the basic randomized SVD. This stuff has been around for well over 10 years now, going closer to 20 actually. So let me talk about some less common topics. So first, let's talk about, so this is a question that I have, some of the stuff I'll be talking about in this next section is also older. I started working on this 20 years ago, actually. But we made some fun discoveries in the past couple of years. So the problem now is to build a very particular kind of matrix factorization. So we started with a truncated SVD. I wanted to find an approximate orthonormal basis for the column and the row spaces, and then approximations to the top singular values of A. Suppose instead you're looking for what I call an interpolatory decomposition. So I want to find a subset of the columns of A that form a good approximate basis for the column space of A. So the matrix C is a submatrix of A. It identifies some columns that are identified by the index vector J. And I use those to span the column space, and then I have some matrix of interpolation coefficients Z. So it's still a thin factorization, but it has a very specific nature. So why should you care about this? So one application of this is data interpretation, that sometimes when you compute an SVD, so if you so in the SVD, your basis vectors are basically combinations of all the columns. Sometimes it's really helpful to identify a few. So it could be that, say you're doing a time series over the evolution of a number of stocks, and then each column represents one stock, then getting basis vectors, or in statistics, they would call this principal components, that are sort of combinations of all of the stocks, has less interpreted. It's harder to interpret, right? It would be easier if you could pick some subset of the stocks that basically say, if you know how these stocks move, then that tells you a lot about how the whole market moves. So that's what I mean by data interpretation. These factorizations, they preserve structure. So if A has non-negative entries, then C has non-negative entries. More important, perhaps, if A is sparse, then C is sparse. And to really take advantage of that, you could do this on both sides. You can have a matrix C that contains a subset of the columns, and then a matrix R that contains a subset of the rows. So if A is sparse, then C and R are also sparse. So you get a very sparse low rank factorization in that case, which can be very efficient. It's storage efficient, that if you use an interpolatory decomposition, you oftentimes don't need to store these matrices C and R explicitly, you just store the index vectors. It preserves the physics. In many cases, this is actually how I started getting interested in these things, that I was working with boundary integral equations where you have a kernel. So these are discretized integer operators where you have a kernel that has some physical meaning, and then the interpolatory decomposition preserves that physical structure in some way. Again, you can compute these things using traditional techniques. So Gram-Schmidt is sort of always my baseline for these things, and it actually works very well in most cases. There is a slight numerical instability that led it to be underappreciated. People tried to use Gram-Schmidt and they got bad results. Basically what happens is the entries of Z blow up. But if you stabilize Gram-Schmidt just a little bit, then you get modest entries in C and everything works very well. But another reason that Gram-Schmidt has been underappreciated, in my opinion, is that there are counterexamples. You can build very special matrices A where Gram-Schmidt provides very poor low-rank approximation. So then people built more sophisticated algorithms to defeat the counterexamples, and they are very nice theoretically, but they're basically never used. Then in CS, this problem has attracted a lot of attention in theoretical computer science. And the idea there, what people find really fascinating are randomized sampling techniques. You pick a number of columns at random, typically quite large. So if you want to find something that's a good comparable to the best rank 100 approximation, you would pick 1,000 columns at random and then try to build something from those. So I will return to that point if time permits. What I've been working with are techniques between a combination of using randomized embeddings and then classical techniques. So the idea is to use an embedding matrix. You use a thin random matrix omega. So in this case, if I want to pick columns of A, I left multiply by omega. So I get a sample matrix like this over on the right. And then the point is that in many cases, if A has low rank, then the linear dependencies between the columns in Y mimic the linear dependencies between the columns in A. So I can now run my favorite expensive column selection strategy on this small matrix Y. So if you can identify a subset of the columns over on the right here, then they tend to also be very good basis for A. So you do the matrix multiplication. You can use structured random map omega. So this is very fast. And then you do some expensive selection strategy over on the right. So typically column pivoted QR. This is what I've been walking around advocating for a long time. And now the more recent discovery that I wanted to flag that I find really fun is that because of the randomization, you can actually run partially pivoted LU over on this matrix Y. And this, to me, is very interesting. So actually, to be strict, you run it on Y transpose. So you pick basically you look for pivots along the rows of Y. You pick basically the largest element of Y, and then you do a step of Gaussian elimination. You pick the largest element of the next row of Y, and so on. And what's fascinating about this is that, in general, partially pivoted LU is not rank revealing at all. You can super easily defeat it. It works okay for solving linear systems, but it's terrible for low rank approximation. But the randomization puts you in a general position so that this sort of very simplistic technique actually works. And the reason you should care is that partially pivoted LU is way faster than column pivoted QR because it can be blocked. So when you run partially pivoted LU from LAPACK, it's implemented as a sequence of matrix multiplies. Almost all the flops are done in BLAST 3. So it's at least an order of magnitude faster. And this we actually didn't discover until quite recently. So this has been really fun. We now have the complexity down to mn plus k squared n for computing a factorization of this type. And it's really tremendously fast. Now we have incremental versions. If you don't know the rank in advance, you can do it block by block and determine the rank adaptively. Right. So related to this question of computing, so you may have, been thinking, oh, this is all fun, but this is a pretty exotic thing. I don't need these IDs or CUR decompositions. I just want the standard ones. And what this slide says is that many of these ideas that I outlined, they actually apply even to standard textbook problems. So if you want to compute a column pivoted QR factorization of a dense matrix, so I mentioned before that this is slow because it necessarily proceeds through a sequence of rank 1 updates to a matrix. So all the flops are done in blast 2 as opposed to blast 3. But if you apply this column selection, this pivoting strategy I described, or this column selection strategy, you can use this to pick blocks of pivots in column pivoted QR. So we actually managed to construct a blocked version of column pivoted QR, which leads to almost an order of magnitude acceleration on a multi-core CPU. So this I thought was really fun. And the quality, I don't show here a graph of the quality of the selected pivots, but they're basically the same. And one way of thinking about this, so pivoting is perhaps, many people consider this a bit of a niche interest that's of interest only to hardcore numerical analysts. But there's an interesting principle here, which is that what randomization does for you in many of these algorithms is that it eliminates the possibility of an edge case. It puts you in a general position where very simple techniques work well. So if we think about solving a linear system, so just a general linear system, AX equal to B, think about, the first technique we teach for this is Gaussian elimination. You use the first row to eliminate x1 from all the others. Then you use the second row to eliminate x2 from all the remaining equations down. And of course, what we teach our freshmen is that this oftentimes fails because the second equation may not involve x2, and then you need to select another row. And this is what the pivoting is. And this really slows things down in practice when you code it, in particular if the matrix is very large. So, and another thing that can happen is that, maybe it doesn't fail outright, but it can fail numerically. That's Gaussian elimination without pivoting. It's very numerically unstable. You may have very small coefficients that you divide by, and all your factors, the numbers in the L and U factors blow up. But it's well known that if you do this on a Gaussian random matrix, then actually you don't need pivoting. It just, of course, this is a probabilistic statement, but with overwhelming probability, the numbers in L and U will be very modest. Now, so what randomization does for you is that you can take any matrix. You cannot construct a counterexample to what I'm about to say, but you take any matrix A, and if you do a random rotation on it from the left and the right, so sort of probabilistic preconditioning, basically, then you're put in a position where you can use Gaussian elimination with high confidence. Of course, if the matrix is ranked efficient, it's going to stop at some point, but it's all the classical counterexamples are defeated. Within reason, like this is not super stable. You have to be, in practice, you have to do slightly more sophisticated things, but this is the general idea. And so then arises an interesting question: how much randomness do you need? So to get perfect mixing, what you would do is you would draw U and V from a hard distribution. So it's a uniform distribution on the set of unitary matrices. So you do basically a completely random rotation. This is theoretically ideal, but it's expensive. Like this has cubic cost, both to generate U and V and then doing the applications of them. So then we get back to this question that we've touched on earlier with a structured random map. So can you do things, can you do rotations that can be applied rapidly, but have enough randomness that you get the appropriate mixing of all the columns? So what you might do is, if you have, say, the system of linear equations, say you take just two of them, you pick two at random, and then you mix them by some random amount, say a random Givens rotation. And then you take the second one, and then you pick a third row at random, and you mix the second and the third. And then you pick a fourth row at random, and you mix the third and the fourth, right? So you need at least one sweep. You need at least n of these Givens rotations before everything has been mixed. So then the question is, how many sweeps do you need before you get enough mixing that the statements that I said hold true? And the theoretical answer is log n. You can show that if you do this log n times log n sweeps, O of log n sweeps, then you get enough mixing, which is nice because then the theoretical complexity of applying U and V then is n squared log n. as opposed to n cubed. In practice, it turns out that 3 sweeps is almost always perfectly enough. So there are curious questions here that relate to random matrix theory and probability theory in interesting ways. All right, so speaking of which, let me say a few words about matrix approximation via sampling. So this is another, so there are basically 2 schools of, or 2 camps that are interested in randomized algorithms for matrices. And confusingly, they both refer to themselves as randomized numerical linear algebra, even though the flavor is quite different. So what I've described is sort of more the traditional numerical analysis approach to things that we've been doing from the math side. When theoretical computer scientists think about this, they have a tendency to think about sampling algorithms. Now, I'll describe what I mean by those. But I'll start by telling you the general characteristics. So everything that I've talked about so far, they accelerate classical methods. But you've seen in the examples I've given you, it's acceleration by a factor of 5, or it could be acceleration by an order of magnitude, or it's from mn k to mn log k, which, you know, in practice is oftentimes not that dramatic, but it's nice, but it's not earth-shattering. But so everything I've talked about so far, it's very practical, it's very useful, but it's not gonna, you know, revolutionize a computation. If you plug the things that I've been describing into an algorithm, with the exception of the single pass stuff, I suppose, that stuff really cannot be done with classical methods. But otherwise, you'll see an acceleration, but it's not like you're gonna, you know, fall off your chair or anything. But on the other hand, it's a perfectly safe thing to do. These things do not behave like Monte Carlo methods. Everything is very reliable. It's very robust. You can get however many digits of accuracy as you want. So the sampling techniques, on the other hand, so in the right column, these techniques behave more like Monte Carlo methods. So I'm going to be describing methods that have lower accuracy, much more variance, and that can fail. But the upshot, why you should, in some cases, be willing to pay this price, is that sampling methods can really lead to dramatic acceleration. They can solve certain linear algebraic problems faster than matrix vector multiply, so basically without even looking at all the entries of the matrix. But of course, then it doesn't work for general data. But in many cases, the matrices have enough structure that sampling techniques work. So let's describe just what is the framing. So typically in a sampling environment, the idea is to decompose a given matrix A into some sort of simpler atoms. So for instance, you could take a sparse matrix and write it as a sum of matrices that each just have one non-zero entry. This is one way of thinking of what a sparse matrix is. You could do it column by column instead, if you want to have slightly fewer terms. Or say you have a matrix-matrix multiplication. If A is a product of matrices B and C, you can think of A as being built up by a sum of rank 1 matrices consisting of outer products between the columns of A and the rows of C. Right, so these are the types of decompositions that people consider. So if you have such a decomposition, now we can use the Monte Carlo technique to sample the matrix. So put a probability distribution on the different terms in the sum up here. And then the simplest Monte Carlo technique would be you pull one of the terms according to this vector of probabilities, and then you rescale the term by 1 over the probability. And then you can very easily convince yourself that the expectation of this matrix X is A. So X is what we call an unbiased estimate of A. But of course, it's a quite strange approximation to A, right? That it could be that X is a matrix that consists of all zeros except one entry of the matrix that now is blown up by a fantastic amount. So it's a very strange approximation to A. But in order to improve it, what you can do is you can draw lots of samples from the distribution and then take the average of them. And then, of course, you have the whole central limit theory magic. That is why Monte Carlo techniques work, that as the number of samples grow, you get not only the expectation correct, but now the variance start to shrink, and your estimate gets more and more reliable as an indicator of what the true answer is. So this has been a source of an enormous amount of theoretical investigations. People have been proposing all sorts of different sampling strategies. How do you pick the vector of probability weights? And at the heart of this work is almost always some kind of Bernstein inequality that says how quickly does your sample concentrate to the average. And basically, for most of these techniques, you get convergence that says basically that the error goes as 1 over root of the number of samples, just like any other Monte Carlo method, which follows immediately from the central limit theorem. You cannot really hope to do better other than in very special circumstances. And the unhappy part of this story then is that the number of samples you need in order to reach some precision epsilon is 1 over epsilon squared. So if you want 2 digits, epsilon equal to 0.01, then you need 10,000 samples. And actually oftentimes 10,000 times the rank number of samples or something like this. So this theory is quite weak in some sense from a practical point of view, but it's resolved a number of outstanding theoretical questions in linear algebra. So from a theoretical point of view, you can get really interesting things. And I think I'll skip this one. Right, so you may have seen, I'm trying to think, what do I need to say? Let's skip this discussion. Basically, there's this notion of leverage scores, which is the answer to what is the best probability distribution. And again, you have a chicken and egg problem there, that if you sample according to what's known as these leverage scores, the optimal probability distribution, you get quite strong theory. But in order to compute them, you need the dominant singular vectors of the matrix. So that's as expensive to compute as, you know, the type of techniques I talked about at the beginning. But there are certain cases where you can estimate the leverage scores and then get powerful algorithms. And now let me get to the upshot of sampling techniques. So I've sort of been saying a lot of negative things about them, but where they really shine is that a lot of the really gigantic matrices, they have internal structure. They don't behave. So the counterexample to a sampling, to basically any sampling strategy, is to take a matrix A that consists of all zeros except a single non-zero entry somewhere. So any type of sample you try to extract from that matrix, you're probably going to miss all of the information. You're going to approximate it by a zero matrix. But most of the gigantic matrices that arise in applications, in kernel methods, in learning, this could be if you approximate a tensor. So if you have a tensor approximation problem, you sort of cycle through each coordinate direction and you try to do a best fit. And the best fit involves a least squares problem with a very, very overdetermined linear system with a coefficient matrix that's extremely tall. But that coefficient matrix has a lot of internal structure. It's some sort of Kronecker product of the remaining matrices, right? So in those cases, sampling can be extremely efficient. It's quite safe. And you can really, by looking at just a subset of the rows and the columns, so you basically ignore the vast majority of the entries, and sampling can really, in these cases, resolve problems that would be intractable without sampling. So it's just the same as for PDs, basically. If a classical PD solver, if you can use finite elements or something to solve a certain PD, then just do that. But if you're in a 10-dimensional space, then your finite element method is not going to work, and you're going to have to rely on Monte Carlo. So it's exactly the same thing here. The Monte Carlo techniques unlock certain problems that you could not, that would be intractable without the probabilistic stuff. You just have to be careful. So if you can use safer techniques, you should. And right, so my last topic, I will just touch upon very briefly. This gets a little bit technical, but I want to mention it because, one, this is really my favorite thing that's happened in my research group in the past couple of years. And also this is sort of where where things started for me with randomized linear algebra. So what I mean when I say a rank structured matrix is the matrix that does not have globally low rank, but it has the property that you can cut it up into blocks in such a way that each block is either small, so it can be represented densely, or it has low numerical rank. So I can store just a sparse factorization of it. Over here on the top right is a typical illustration. So this is the simplest form of what's called a hierarchical matrix. So you just take the original matrix, you cut it in 4 pieces, the off-diagonal blocks have low numerical rank, and then you take the diagonal blocks and you repeat, you cut them in 4 pieces, the off-diagonal blocks have low numerical rank, and so on. So matrices of this nature, you can store in almost linear complexity. You can do the matrix vector multiply very efficiently. You can do an LU factorization, actually an exact LU factorization of a matrix of this type in basically linear complexity, and so on. So you can do a lot of operations very fast if you have a matrix in this rank structured format. And these matrices, they come up all over in scientific computing in particular. So they are the solution operators to elliptic PDEs. Like you may recognize this if you're familiar with Calderon-Sigmund theory. Like it's basically the linear algebraic equivalent of that. So things like Dirichlet-Neumann operators that come up in domain decomposition methods, scattering matrices. If you work with, radar or sonar applications, these are really important. They come up in inverse imaging, all sorts of things. And importantly, in sparse direct solvers, you get these larger Schur complements, like larger and larger dense matrices that arise when you try to do an LU factorization of a large sparse matrix. And these dense matrices oftentimes have this hierarchical structure as well. Okay, so this is why you should care about rank structured matrices. So now the question is, just this slide to prompt you that the tessellation, the specific geometry of the matrix on this slide is the simplest possible one. In real applications, they tend to be more complicated. There are much more blocks that need to be represented as dense and so on. So I'm giving you a very abbreviated story here. But so now the question is, can you use randomized techniques to build an approximation to a rank structured matrix? So the setup here is that you're allowed to draw some test matrices, omega and psi. You probe the matrix with those test matrices, you get to see the samples that come out. And then the question is, can you rebuild the matrix A from just looking at those samples, Y and Z? So the randomized SVD that I described in the first 10 minutes fits in this pattern. Here is how that would be coded using the notation. And basically, so I'm running out of time, so I will just tell you in words that this can be done as well for the rank structured matrices. You can build specialized matrices, omega and psi, that are designed specifically for the tessellation patterns of A, in such a way that you can build approximations to all the off-diagonal blocks and to the dense blocks in basically linear time. And I find this really cool and would be very happy to talk to you offline about this. So basically what we did several years ago, Lexing Ying and Lin Lin and Jianfeng Liu built an algorithm that solved this in principle, but it has very, very high prefactors. So we've improved those prefactors a little bit, but they are still pretty bad. And then for a slightly smaller specialized case of matrices, which are the Hodler matrices that I started with, and also hierarchically semi-separable matrices and a range of more specialized formats, we can actually do this in truly linear complexity, fully black box. And these things really fly. And it's very cool. But I will skip all that. So just here is a summary of the talk. So I think I'll just leave this slide. So I should have mentioned these slides are up on my website in case somebody wants to revisit. So here are just the key selling points for the randomized SVD. What we're working on now is high performance implementations, really coding these things up, because you notice that there are all sorts of parameters in these things. Should you use power iteration or not? Should you use oversampling? How much oversampling? Should you use structured random matrices or just Gaussians? So we're trying to automate this. So the idea here is to build an approximation to the spectrum of the matrix, because this really tells you what algorithm is most efficient. So you want to get black box software for this. I'm working on techniques for building full matrix factorizations. I have these rank structured matrices that are moving really fast at the moment, and connections of this to PD solvers. And then starting to look at applications of these ideas of randomized low rank, randomized dimension reduction on applications outside of linear algebra. For the last slide, let me just point you to some surveys that we have. There are various tutorials, summer schools available as videos, and we have software as well. So thank you very much.